Hello, I'm Ty Frazier, and my co-collaborator on this project is Don Wilcox. What we've been doing and working on is creating surrogate models using deep learning for nuclear reaction systems. And today we're going to present our progress that we have made in that and the challenges that we have met and how we're attempting to overcome those things. We are from these respective institutions. What we're first going to get into is the origin and the reasoning for wanting to create these surrogate models. Where this work is being done at is at the Center for Computational Sciences and Engineering, CCSE, at Lawrence Berkeley National Lab, LBN. They develop something that they develop is AMRX, which is a block structure adaptive mesh refinement library. And you can think about something like that is if you were doing a fluid computational fluid dynamics simulation, and you were to place a object inside of the domain, and then the fluid is going to pass around or atop this object. The closer it gets to this object, the more refinement simulation will need, mesh refinement simulation will need in order to accurately depict the system as the simulation moves forward. Something that CCSE develops something that they developed that is AMRX based is multiphysics PDE solvers for various areas. But the one that is most applicable for us is for astrophysics. And the thing about multiphysics PDE systems, though, that are I guess you can say you would like to be better at, is the fact that they're very computationally expensive. And the reason for that is largely because they're having stiff ODE systems, for example. There are other reasons why you could have a lot of computational time for these systems, but for the ones that pertain to us mostly, it's going to be for the stiff ODE systems. So some examples of astrophysics simulations that require nuclear reactions. On the left, we have X-ray burst flames. We're up in the top frame here. You have temperature, where the darker it is, the hotter it is. And then this translates into the energy frame in the middle here, where the more light green, yellow area, the more energy is there. And this is the reaction. This is the result of nuclear reactions that cause this X-ray burst to happen. Then we look over on the right, we have white dwarf convection, which the convection is caused by nuclear reactions that happen in the center of this white dwarf. And if you were to run one of these simulations, you first need something like these red cells here, which is the most coarse and unrefined mesh. And then as you start to get closer to the white dwarf, you start building you have on top of that mesh a green, more refined mesh. And then when you get to the center where all the nuclear reactions are happening, you have a black, most refined mesh of the simulation. And this is a 3-regime mesh where you go from red to black in terms of coarse to more refined in order to accurately depict the simulation. And this is where AMRX will be a base for building some solver for a system like this. And the reason nuclear reactions systems need a surrogate model for us is because they are usually the most expensive part. For example, in X-ray bursts, they take anywhere between 50 to 75% of the computational time and expense. So if we were to develop a surrogate model for these nuclear reaction ODEs that was able to retain the accuracy of the numerical analysis scheme, while at the same time, because of the fixed computational time cost after being trained, we were able to make these simulations happen at a much faster rate with the same accuracy. That is the idea of making these models. So the system that we really want to make surrogate models for is a hydrodynamics PDE system that CCSE the simulations with. And how they do these simulations, they use a split and composition method called the string splitting, where they're able to split the hydrodynamics PDE into the hydrodynamics or the advection and the nuclear reaction system of ODEs as subreactions here. And how this simulation will work is that you will advance your the nuclear reactions part of this split half a time step, and then you will do a full time step of the hydrodynamics split, and then you will do another half step of the nuclear reaction split. Now, why the nuclear reactions, because they are so stiff, the reason that they take so much computational time is traditionally they'll be used with something like an implicit multi-step ODE integration. And these things can take a lot of time to, they're necessary to have accurate results with these stiff systems, but they can be very computationally expensive. And there are more accurate coupling schemes that exist aside from string splitting, but all of them still require for 1 and 3 that we use an implicit ODE integration, as that's what's going to take to actually solve the numerical reactions system, the nuclear reaction system, because again, it's very stiff. And so because each step is so expensive and we have an adaptive time mesh as we go along, it's also very hard to load balance. So in between any 2 time steps, the number of multi-steps needed, it's going to vary. And that could be part of the reason why it can be very hard to load balance everything. And generally running these, now so it makes it all these multi-steps in between these steps make it very computationally expensive to go through each from time step to time step. So this is the reason why it's computationally expensive, and this is what we want to retain the accuracy of, but be able to speed up the simulations by creating a surrogate model off of. So our approach to doing this with neural networks was inspired by the Physics Informed Neural Network paper by these authors, where in this paper, what they do is they create surrogate models using neural networks for PDEs. And they have 2 approaches to doing this. They have the continuous model, which is pulling all of the PDE to one side of the equal sign, where you have your temporal operator and you have your spatial operator, F. And you plug this into your loss function, and what the approach is able to do and able to accomplish was able to progress over the entire solution space, given any point in solution space, and given that time, it was able to get to the next point in time, next point in space. But the downside of these is they take much longer to train, and take a lot more observations to train them. And then the other approach was the discrete model, which is very fast, takes a lot less observations, and a lot less time to train. But their drawback comes from how what you do is you plug in your U, but their loss function is based off of you create of taking your spatial operator, throwing it into a Runge-Kutta scheme, and coming out with Q+1 U's. And the reason, the drawback to that ultimately has to do with the idea of Runge-Kutta. It has a predetermined time step you have to put in. When you run Runge-Kutta, it has a delta T. And so you have to tell your neural network while training it what that delta T has to be, and it doesn't change. So the drawback is the predetermined time step, which isn't a drawback if you only want to see certain snapshots throughout your simulation, and you don't have an adaptive time mesh you have to worry about, or if you're just trying to run off to the end of your simulation, these things would be great. But for us, where we have an adaptive time mesh, and we also have to worry about seeing, we need to see each point in our solution space. We can't just look at every, so in their case, every 0.8 very well. We can't make those kind of jumps. So for us, we need to go the continuous approach, and that's the approach we have taken. So before we get to our larger system that we want to try to create things for. We wanted to start with a very simple problem that had something similar to that of um, in the something of that similar to the physics informed neural networks paper, and things characteristics that were similar to our larger system. The reason we want to start with something, I guess, very similar to the physics informed neural network paper is because, I mean, they have done it, but we're dealing with a different type of dynamical system. ODs and PDs are just different. Um, so what we did in terms to make it similar to their paper is just in their paper, what they do is they get essentially like a wave that moves forward, a wave front that moves forward for a PD simulation. So kind of like a trajectory. And for this, what we have is a trajectory as well that we're going to train and test on, just as they did in that paper. So that's our basis of commonality between the two things, between this problem and their paper. Where we're going to differ and where it's have some similarities to our overall system is that we're going to have an exponential decay, which is a characteristic of what's similar to the idea of having the temperature in our system actually has an exponential growth. And we have in our target system a conservation of the mass fractions that equal to 1, which how this is set up, given these initial conditions, we have a conservation of the x0 plus x1 is equal to 1. So we have certain similarities that we're trying to put into this simple problem, while also certain similarities with the paper. So what we did for our components, so this is our actual system. This is the analytic solution. These are our initial conditions. And what we picked for our loss function is that we had 2 error components. The first error component will be this side of the system minus the right side of the system. But ours will change from that end of the paper. I'll speak to that later. But so we still have the what would be on the left side of our loss function would be our prediction, then taking the gradient with respect to t of our system, minus our right-hand side, which as you'll see in the paper, they also have their prediction in the right-hand side. Instead, we're going to use the actual values on the right-hand side. And then our other error component is just a point-to-point prediction minus actual value. So those are our 2 components to our loss function. So we then come to our results here. And so what we did, just as then, we're training and testing on a trajectory. So what we took, so the what would be the x0 and x1 trajectories, we took a subset of those to train on, subset of those points to train on, and then predicted the rest of them. The analytic solution for these, the dots is the x of t's, and the predictions are the solid line p of t's. You can see that they overlay on each other very well, very well to the eye. And then we have the acceptable loss, values for us, and what would be acceptable loss value for the overall target system of having 10 to the negative 3 or under would be an acceptable loss error and error of accuracy difference. So we see the solutions lie over top of each other very well. Then we go to look at the gradient here. So in other words, what you're looking at is sort of the dashed lines and the dots would be our second error component. So that would be dp dt, which is the left-hand side of our system, minus the right-hand side, f of x of t, where f is just the operator for the right-hand side of the system, plugging in the actual values x of t, and seeing how those 2 individually evolve over time. And we also have in this solid line here would be again the operator for the right-hand side, but instead of the actual values, we plug in our predicted values. And we see in the end, they all do seem to overlie on top of each other, which is really nice. We also means that our error component it gets very, very close to 0 over time. So that's good. But the reason we picked this as our second error component, as opposed to how they did in the paper, and this would be their error component, we noticed that if we had the system that the neural network had to predict both sides of the system with P, that whatever local min it got to, or how fast they got to the best local min we could find, would be highly determined by its just initial guess into the error space as it started to trek down using gradient descent. However, versus we noticed if we put in x of t, that we would always get much faster to a local min that was as low or lower than anything that we could do when the neural network had to do the prediction for both the left and right side of the system. So this is the reason we chose this as the second component of our system. And then in this third frame here is the error frame, where you can see the training in blue, the test in the dashed line, and our second error component here in green. And then you can see around 220, 230 epochs, we've met our target objective of error threshold, what we would need for our system. So this was good to see here. So now with this motivation, that we were able to come something that one had a basis similar enough to the paper and had certain characteristics similar to our target system. We wanted to then try a more complicated system, the CNO cycle, or carbon, nitrogen, oxygen cycle system, which is a nuclear reaction system. It's more complicated. We're going to have more trajectories, but at the same point, we have what we're trying to see is, we're still something simpler than the target system that has 70 or so dimensions, has a lot more. It's going to have, and I'll tell you why, more nonlinearity, and has what we don't have. Our temperature will not evolve in this CNO cycle, but it will in our target system. So now we're making another step forward and progressing toward our target system, and making it a lot more complicated in the beta decay system. But we still don't have the full complexities of our target system, and this will help us to anything that we come across and tackle. Would help us more getting to that target system of knowing kind of what's there. So the isotopes we're going to deal with are these 7 plus hydrogen and helium-4. How the system looks is you'll have some mass fraction to represent your isotope x sub I. dt equals f sub I, the operator for the right hand side of the system, of f of x. And another thing which our target system and this system also have is a sensitive dependence upon initial conditions. So another difficulty and complexity to tackle as well. So the data that we use to train and test our neural networks on, how we've initially got this data is that we took 1,000 simulations, and each of the simulations, how they differ is that how they're set up is that each mass fraction initial portion is the same, but what we change is the temperature, which ranges inclusively from 10 to the 8th to 5 times 10 to the 8th Kelvin. Remember when I brought back the idea of having the non-linearity, that brings back the idea of us changing temperature. Because if you go back and look at our system here, what you see in these down right arrows, these are the weak force reactions, which are non-dependent on temperature. But all these other reactions where you see carbon-12 going to nitrogen-13 are dependent on temperature. So what we're changing is the overall speed, reaction speed of our trajectories of our system by increasing the temperature of our system. But what this also causes is us to have smaller time steps and smaller overall time trajectories, time needed for our simulations to reach similar overall evolution of our trajectories with higher temperatures. As the temperature changes and speeds up our rate of reaction as it speeds up. So the structure of the neural network that gave us the most success is what we're going to go into now. Where if you're unfamiliar with neural network, what it looks like is something like this, which was taken from this book by these authors. So the things that we didn't change or play with at all was our 11 inputs, which is our non-isotopes plus time plus temperature, plus, and then we have output. Our output was all prediction for all mass fraction isotopes. So the structure that gave us the most success early on was we had 4 hidden layers. So there's 3 here. So imagine a 4th one here. And then at each hidden layer, we had 100 units. So in other words, so this is at layer 1, this is 1 unit. We had 100 of these per layer for all 4 hidden layers. And then for activation functions, if you were to take this to be hidden layer 1, 2, 3, and 4, so if it was labeled 1, it would get sine. If it was labeled 2, it was cosine. So in other words, if it's an odd labeled layer, they get sine. If it's an even labeled layer, it would get cosine. And these activation functions gave us the most initial success. So, and the loss functions that we've put in here. So we have 3 of them. We have a point-to-point L2 loss. So in other words, our predicted minus the actual, and taking the L2 norm of that. We also have our conservation of mass, where all the mass fractions have to sum to 1. So we take the L2 norm of that. And just like we did in the beta decay system, where we differ from the paper, we do a predicted mass fractions from our neural network, and then take the gradient with respect to t to get that value, and then we minus it by the taking the actual values for the right hand side. So again, f sub I is our operator that gives us, if you put in our x's, it gives us the right hand side corresponding to that particular mass fraction. And so for us, we use the actual values for these, as these are our 3 error components. So if we look at these, some initial, like how we did with these things, we had some good results and progress where we could see here for oxygen 14 at almost, we'll just say 3 times 10 to the 8th Kelvin here, that for open circles in our predictions and blue dots being the actual test data to go against, we see that they're very close, no more than 10 to the 4th off from one another. But what we don't have and what we didn't get, it was like this little bump you see here, right? So it didn't really depict the full behavior. It got close in point to point wise, but it never had that initial evolution for it to actually stay on track, as these initial points seem to actually be around top of another. And then if we look at our system error, or our 3rd component error for oxygen 14, we can see that it's all fairly low, 0 to 115. So for 100 points in each of these 1,000 trajectories, which I forgot to mention, that so each of these points, that's 100 points added up in terms of error at each of these simulation points, and this is as high as it gets at this temperature of 3 times 10 to the 8th. And overall, it seems to be fairly low, but what we would obviously like to fix is early on you see the error much lower, and it seems to, as temperature rises, our error increases. And obviously we would want everything, even though this isn't that really that high, we would want it to obviously be more close to 0. We want to be able to make this very consistent of how this is close to 0, so then all of this would also be close to 0, even as the temperatures increase. Where we need a lot of progress, and we realized we had a lot of challenges that we need to overcome, is when we were dealing with, we could look at helium-14, which had a lot more evolution into its trajectory over the temperature of 1.01 times 10 to the 8th, as has this linear progression. Our prediction doesn't have any type of linear progression prediction. And we honestly think that if we were just to take this and stretch this out further in terms of epochs, that this prediction would have almost became a solid line, while it didn't capture any of the actual behavior of helium-4 in this case. So that was something that really hit us as an alarm, that what's going on and what are we doing? So one of the reasons we thought about this, so we need to These are obviously much different scales. If we look at, for example, helium-4 and oxygen-14, however much is little bit it moves is like, we'll say 10 to the fourth, and this moves at 10 to the 2, -2. And you could, that difference in scaling, we're not accounting for in our error, right? We need to learn to scale our error correctly, so scaling these isotopes and scale our error correctly, such that we're better able to capture the evolution, and also taking our time simulations and actually making them go much longer, so that we have more evolution in our trajectories. So then it could start to capture, our neural networks could start to capture the different dynamics that will happen throughout the system, as opposed to if most of our isotopes aren't scaled correctly, and we don't have enough evolution in our actual trajectory for these isotopes. They just look like they're going in a straight line, and then our neural network doesn't really start to capture evolutionary behavior. It just learns to go and capture this straight line. It doesn't have a lot to go with. So then we have some simulations where, like, a trajectory of helium actually has quite a bit of behavior. It's like it's undersampled, like you would think of in a category, a classification problem. If it doesn't have enough for it to go by, it learned everything. It learned and scooped toward everything else. Even though, like, this has much more error, so it skews more toward helium-4 because of this larger error, but it didn't skew toward that behavior. It skewed toward behavior of this nature. But then again, also, if we look at our system for helium-4, we actually have an overall smaller peak in our error as opposed to oxygen-14 for system error. But again, we still want to get everything close to zero here, and we still have that trend of, as we increase in temperature, the system error for helium-4 also increases. So now if we look at our second component, our second error component, the mass conservation, we see that our predictions are really starting to converge to 1.02 over all these 20,000 trajectory points, which is 200 trajectories, because we have 100 points per trajectory. But obviously, even though it's starting to converge to 1.02, we would like this to obviously be at 1. So we have a lot to fix there as well, things we want to improve on. So summary of challenges and how we are going to try to attempt to overcome these things is that we're going to have longer trajectories. So the isotopes themselves evolve more over time in our system, and we can train on that so it has more behavior for it to learn off of, the neural networks do. And we need appropriate scale the isotopes so that their difference in error and prediction versus actual doesn't skew one way or the other. As you know, skewing, this is any error here, this is on magnitudes of 10 to the -2, as opposed to error here, we'll say at most at 10 to the -4. So it's going to skew its error to learning to things like this, but it's learning more of its behavior of things like that because that's what it's mostly seeing. So we need to skew, we need to get rid of this skew by scaling our isotopes or our error appropriately. And then we have some problems. So with the actual numerical scheme itself, can produce some issues where sometimes the isotope, it can have non-physical values where the isotopes go below zero, or have this jitteriness that it seems to bounce up and down. Which this is what happens in the actual system, and there's ways to kind of correct that for that. But we need to smooth it, figure out the way that'd be best for it to smooth for the neural networks for them to learn the best. So we tried some of that. This is kind of like early approach. We just, so in early ways of how we're trying to overcome some of those challenges. We did increase our trajectory some, and then we, so this one, so what you saw was our reaction. If you were to take that as 1, this is 20 times the length of that in terms of the actual overall time that went across. Or correct me, 10 times that. I apologize. So instead of 4,000 some points, we have 40,000 some final time point, and we have more time points per trajectory at 1,000. So we magnified the time by 10 and magnified the number of points per trajectory by 10. And we just wanted to see if we could first start to take a single trajectory, and we need to first capture the correct behavior and movement of each of the isotopes as well. So we also started to do some scaling of these isotopes. We also even changed our neural network structure. Our neural network structure was then just we got very simple. We just went to one hidden layer, 10 nodes in that layer, and we changed our activation function that is giving us the most success right now. It's hyperbolic tangent, and we made that. What made that change more successful was our scaling of time as well. Now our max time only goes to 1, so it doesn't saturate as bad. So we were able to go through and scale all of our isotopes. And what you see is just the how well it learned this single trajectory. This will be the longest trajectory in the system, so it should be the smoothest in terms of time steps needed and stuff in this matter. And what you see is it was able to do a lot better with capturing this linear behavior and able to capture some weird things. Now, like there's these weird like jumps and spikes that you have, and this is just from the integrator in and of itself. But the integrator seems to correct itself. So you see this weird like up and down you have for carbon-13, but then it evolves over time in a more smooth manner. To which if you look closely here with our neural network, the prediction it goes around this line. It's not strictly this line, but it's going up and over and around this line. So it's really capturing that overall drift behavior. It's just not directly that line yet. And you can see that kind of all these, they kind of have a up and down kind of motion where they haven't specifically just captured that line, but they have the overall drift, which was nice to see. And they lay over a lot better, and actually capturing that behavior was really nice to see, honestly. And you can see this also with carbon-12. And so the longest trajectory obviously would be with the lowest time because it would have the lowest reaction speeds. So this is with 10 times, it would be 10 to the 8th Kelvin is what temperature these trajectories are for. And now you can also see this for nitrogen 13, 14, 15, and oxygen 14. You can see that there's a little dips there that it doesn't, as tightly go up and around the points around. But largely it's even starting to capture, like it comes down, but it's not really going this up and down spike that the integrator seems to have. The nitrogen 13 here also seems to capture this on the way down. And in terms of smoothing data, this is what we were talking about in terms of, so you see this can be something that the integrator can actually cause. It'll bring back a lot of things that has a lot of jitteriness along the trajectory. And we learn how to, this is something they encounter in the actual simulations themselves with the hydrodynamics, because it's the same. They also use VOD, just same thing we use for our simulations, and they have a way of doing that's really good for that simulation. Well, we got to figure out the best way to smooth this data that will help us best with the nuclear, with the surrogate model for the neural networks themselves. But it still captured that overall drift, which is really nice. It come below. It started too low, but it still had the overall idea, which is nice. And oxygen 14, you can see it shoots too high up here, and then it comes back down, and then it settles in, and it's still pretty good. And the same thing is true for oxygen 15. You can see better where this kind of goes, seems to go up and around pretty much that point, the actual point around it, but it is capturing that overall drift, which was nice. And again, for oxygen 15, it actually, still shoots a little low, but again, the overall trend it caught, it was nice to see. And as you can see, this is on like 10 to the -4th movement, 10 to the -4th, 10 to the 2nd, just these different magnitudes of movement was something is what we're trying to overcome and scale. So then after we got this right for like one trajectory, right, we want to see what we can do for 2 trajectories. So now we've also scaled temperature as part of this, right? In our previous single trajectory here, all you're seeing is like a point to point. We've not put in the bells and whistles of learning the vector field yet. We wanted to see how well we can just learn some trajectories and what we need to do, right? And that's kind of where we're at with this. We just kind of really got to this point with this second part where we're now doing more than one trajectory, since we have these trajectories right now. From the first one, we have kind of where we want to be. So now our input is also it's not just time, but also temperature, right? So if you look back at these versus our original neural networks, it has 11 inputs. This only has one, and it's just time. This has now two inputs. It has scale temperature and scale time, right? That's how the temperature really delineates which flow you're on in the solution space, and the time just tells you where you're along that flow. So if we're only dealing with one flow, time makes sense as only one input. We're just going along that flow. When we add more flows, we need to delineate. We need to figure a way to tell the neural network how to delineate between them. So where we're at now is in terms of how the neural network itself is constructed. It has a scale time and scale temperature, and the single ones we got really right a minute ago. If you look at these now, they're actually a little bit worse. As you can see, it still seems to capture somewhat the behavior, but it's mostly it didn't seem to curve that well. It seems to be mostly like a straight line all the way through there, which is not really good to see necessarily. It's not as much just tightness around the actual solution, and it's always true. This is what you see of the first ones. It's like a little bit worse. And then if you go on to what would be not the new trajectory that we hadn't shown yet, this is now for 1.12 10 to the negative eighth with 10 to the eighth temperature, which is true for both of these. That's just mislabeled. My apologies. And you can see that the error seems to be much worse for those. Now, overall, this is still much better than we were doing in capturing some of this evolution. But this is where we probably need to start adding those bells and whistles so that it can better help learn these different trajectories. This was just, we were trying to see as we was able to learn this first trajectory. So we literally ran this last night just to see what it would do. So good or bad, we were going to talk about this. And we could see, it still can delineate between these two trajectories overall, which is good. But it doesn't capture these trajectories as tightly or as nicely as they did before. And you should notice, I forgot so this is on scales of 10 to the negative 7, right? You see what we see for carbon-13 is much smaller than what you have for protons or hydrogen, P. And that's the reason for needing to scale. Or nitrogen-15 is 10 to the negative 8. And here, so 10 to negative 6 versus 10 to the 2. So the magnitudes are much different. So the scaling is what we're really trying to get right. And even if you look at this one here, where it seems to be really off, it does capture where it kind of shoots up, comes back down, has a little hump. It just never quite gets there. But it's capturing the behavior much better. That's what we really liked about this. This was a good sign in that extent, but it doesn't as tightly capture around the actual point as what we did with a single trajectory. So this is where we're going to start adding in more bells and whistles and maybe trying different scalings and stuff like that, because we kind of got it where we want for this one trajectory. So now we want to try to do it for more and more trajectories. So we're going to first start that with 2, see what and build from there, and then do as we need. And then that's where you saw it kind of did bad. Here's some places it pretty much did as well for the double trajectories. For the nitrogen-15, you can see it pretty much does the same thing for this one as it did for the single trajectory, and it still captures it very well. What you see is more prominent is, even though this slight increase in temperature in terms of versus 5 times 10 to the 8th, this has a lot more jitteriness in its actual solution. And this is the thing we're talking about. We need to figure out how to better smooth this out for the neural network. And then if you look at oxygen-14, again, this should also be 1.1 times 10 to the 8th. since they have a kick up here. Oh, so this is the same thing. I apologize. This one was just a mistake on my part. But if you had seen this, what you see for this one is it goes to 0.0014, and because it's higher, it had for the second trajectory. You see how there's this little kick up here. When we look at that same trajectory for the 1.12, it actually kicks up to 0.14, and it has about that same difference. Then it seems to have scaled and got much bigger for the first trajectory, but it still does a good job, at least tightly and overall capturing the behavior. But the shoot up, or it's trying to capture this weird thing the integrator is doing, and uh, it shoots by a lot higher. And that's because for 0.14 was actually has, that's now the max. So in terms of scaling it still differs by about the same amount. So for the second trajectory, when we do the double trajectories, so for the 1.12 actually has this much kind of like off the cuff from where its starting point to where it's going. It's overshooting, it looks like. But that increases for this one, because the 1.12 actually goes to 0.014. So it's slightly bigger, and it's caused the ones that were slightly smaller to have a bigger uptick. And that's something also that we're just going to look at, start with both these trajectories and figure out how, as you know, even during that time period, the trajectories don't have the same overall like maximums, mins, and stuff like that. Like their evolution is fairly similar, although it might have a lot more jitter in this, or this one seems to have a lot less evolution here than this one does, for example. But that's something we're just going to have to figure out. That's something in between when we start to get to these different flows and these different trajectories. So that's part of the scaling issue we're going to have to deal with. We were able to get it from one trajectory. Now we're going to start work for two, and so forth, and see if we can figure out a pattern to which, given these different trajectories, we're able to scale so it's accurately able to capture everything. So in conclusion, our problems are different than what they faced in physics and informed neural network. We have to face some things they didn't have to tackle. We're having to face multiple trajectories or multiple flows. They have PDs, we have OD systems. We have to worry about things that are very stiff. So it makes a good research problem because, it's not something they had tackled. They did great work there. It's just we're tackling difficulties that they didn't have to encounter for their problems in that paper. We got good motivation that we were able to get things that almost work perfectly with the beta decay problem, as it shared a basis of common similarity between the paper and our actual target system. And we were able to make progress in the CNO nuclear system. But ultimately, but we still have ways to go in that, as you see. But once we figured out the CNO nuclear system surrogate model, we're then going to expand to the large 70-dimensional system. It has a lot more nonlinearity, still has a sensitive dependence upon initial conditions, and it's even more stiff. But that's where we're at. We're facing some different difficulties. We made some progress that we like to make us believe we can do the more target system, the system we are doing. And once we're done, we're going to tackle essentially the same family of systems, but a more complicated nuclear reaction systems. Just a note, this work was funded by the NSF and the NSF MSGI program and ORISE. Thank you very much for sponsoring this. And this is their message to, they supported this. So thank you in conclusion. If you have any questions, you can email me here at Frazier197@umn.edu, or you can email Don at dewilcox@lbl.gov. Thank you.